And this is the DiffEQ review for exam 1 for through SIGEP, whatever. All right, this is my email in case you have any questions about anything at all relating to this, or even, I don't know, anything, whatever. So the way I like to do these reviews is we're just going to go topic by topic. You guys can ask questions on anything at any point. So don't feel weird if you have a question about separable during when we're doing Bernoulli. You just look like an ass, but I would answer it, and you guys would know something from that. All right. Here's the topics we're going to go over. Apparently, nobody knows what exactly is on the test. So usually they give you a review sheet, but they didn't. So I'm just going to wing it. So far we got separable, linear, Bernoulli, exact, and then whatever else you guys have to throw at me. So that means any examples of anything you found in the homework. Don't ask about a tank problem, because I don't know how to do that. But I'll try my best. I was like half kidding. I could figure it out. And like anything else is like a bunch of other stuff. Like weird questions is like largest interval that something exists on, or if you have a question on that. But I doubt that would actually be on the test. So the main thing you guys want to focus on is these 4. So if you know these 4, you'll at least get like an 85. So that's a good thing, right? Who knows what else? They usually throw like one weird like part D of a question is just like, if you were instantaneous this and continuous and whatever, and then it is like derivative. And it's like no one knows what's going on. All right, so enough of me blabbering. Let's get started. All right, one more thing. I made a Excel where you guys either at the end or if you have to leave during the middle, I won't care, will put down your email. And then I will send you all the notes from today and the notes from the exam 2 and exam 3. So basically everything. And from that you can study. It's good. I wrote down like the steps for every single kind of problem. So hopefully it maps it out pretty well for you. Okay, so like I said, any questions, just raise your hand and say, hey, Pat, and I'll be here for you. All right, so let's start off with separable. Well, actually, let's start off with what exactly a differential equation is. So like, I don't think they actually said that. I remember when I took the class, it was just like, here's an example. This one you call it separable, and just y equals. And it's just like a whole bunch of math on the board. It's like that thing where it's like math and it, what was I getting at? Fuck it, never mind. Okay, so differential equation, what it is. It is an equation or a expression of whatever which has derivatives in it. So like a dy dx, a d2y dx squared, could be 3rd order, 4th order, whatever it is. So it has some kind of derivatives in it. It could also have x's, y's, z's. It could have other stuff. So the point of this class is to learn different methods of getting things with a dy dx, a d2y dx squared, whatever it is, to look like y equals, or to get the derivatives out of the equation to either give you y equals or some implicit solution of y's and x's. So you want to end up with no derivatives. That's the entire idea of the class. So if you guys didn't know that, now you do. All right, let's get into it. Separable. So separable is pretty easy. You just literally separate the variables and integrate. So we'll start off with an example with that. All right, so the first example will be, and all these examples are off of old tests. I don't necessarily know which year, because I kind of took them from every year. But yeah, I didn't make them up. So if I made them up, it'd be crazy. All right. So we have 2x cubed y dy minus, in parentheses, 1 minus y squared dx. And also we have an initial condition, otherwise known as an IVP, initial value problem. So initial value problem, I know they use that term a lot. It's not a different kind of problem. You could have initial value problems of separable, linear, Bernoulli, or exact. They're just, after you find, like, there's a constant and your answer, it's basically giving you a condition to put in for x and y to find that constant. And then you just rewrite it with the constant instead of the c. So it's really nothing to be intimidated about. All right, so here's our thing, our separable. So the first step is to just try to see what it is. Make sure it's separable. All right, so you have a term with y's, just y's in it, good. This has an x, this has a y, this has a y, this has an x. Or and 2 is just constant, whatever. So if you move around the right stuff, you can separate this and then integrate. So let's do that. I'll do a little magic trick. Take away the equals and then put it right there. Right? Let's save some ink. All right. So now we could, let's see, what can we do? We can move this y term underneath the left side and then move this x term underneath this side. So let's do that. I'll put the initial value up over, or right underneath, and I'll go to the left. All right. So let's do that. So you have y dy over 1 minus y squared equals dx over, and I'll put the 2x cubed there. So I'll put the 1/2 in front, and then x cubed, like that. All right. So pretty straightforward. So now after this, there's one little tiny rule with separable in case it gets really intense later on. You always want to make sure you have your dy's and your dx's in the numerator, because that's the only way you could actually integrate them. Because if you have them in the denominator and you put an integral in front of that, it doesn't really make any sense. There's no really way to integrate that, at least that I know of. So you got that. So we could just put integral signs in front of it. And then we could, let's integrate the left side. So you have, so you have integral of y, I'll rewrite it, y 1 minus y squared dy. I don't like this marker. I want to try to get see if there's one that's nicer. All right. So for an integral like this, what integral method, go back to Calc 1. What integral methods ring a bell right here with this? Anybody have any guesses? No? I heard u sub. Someone just said u sub. No one said u sub. I made that up. But u sub. U sub is the answer. All right. So now I may have just freaked you out with like, oh my God, we got to know all that stuff. You don't if it's really like the integral of trig functions, integral of like t e to the x or t e to the t or something like that. They're going to give you an integral sheet where you have a lot of these integrals. But something like a simple u sub, I think you should be familiar with at least for this and math later on in your engineering careers. But we're right here and right now, so let's solve it. All right, so we're going to make u. OK, that marker works less. Try this one, Quartet. That's usually a good company. U, that's the same. All right. So 1 minus y squared. So then the du is going to be negative 2y dy. OK. We don't have a negative 2y. All we have is a regular y. So we can move this negative 2 to the bottom. And we have du over negative 2 equals y dy. All right. So now we have everything we need to substitute in. So we have the u equals 1 minus y squared, which is in the denominator. And we have the y dy, which is in the numerator. So let's do that. So this turns into the integral of, where are we at, of du, or this over negative 2. I can take that out, put it in the front, like that. Put in a negative 1/2 in the front. And then we have the 1 minus y squared, which is simply just u. OK, so I better get an answer here. What is the integral of 1 over u? Yes, everyone mumbled natural log. Yeah, natural log of u. Good. So natural log of u, and I'm going to just go right to substituting it in. We know that u is 1 minus y squared. Was technically the natural log of the absolute value. Ooh, you got points off. Aha. But no, they won't give you points off for that. I don't know, they might. 1 minus y squared. I'll put absolute value, whatever. I'm sloppy. Sorry about that. Hope you can read it. So do that, and then it's over negative 2, because you get the negative 1/2. And then you can add a c, plus c. Plus c. So that is your answer for the, actually, wait, hold on. I forgot we were solving the left side. Left sides, you don't usually put the plus c. Let me explain that. When you're integrating both sides, you really want to put the constant. You can put it wherever you want, it's correct. But you really want to try to put the constant on the right side, or the x side. Because if you can keep it there and leave it there. Because if you're trying to get y equals, you don't want a constant to deal with here that you might have to move over, and it might get complicated. You might mess up a sign. So just just have safe habits, put it on the x side. OK, so we're going to not put a constant here. Yep. Oh, wow. Thank you. They're brighter colors. They're more happy colors. So that's good. Perfect. You saved us. All right. So that's the left side. Now we're going to do the right side. So the right side is the integral of, I'll put 1/2 in the front. And then you have x to the negative 3 dx. All I did was take the x cubed and bring it up. So then this becomes 1/2 x to the negative 2 over negative 2. And then I'm going to put a plus c on that side because this is the x side. And then this can simplify into x to the negative 2 over negative 4 plus c. All right. So now we have the left side and the right side. Yeah. OK. Yeah. OK, so let's put this all into one equation. Where's the left side? The left side, so natural log of 1 minus y squared over negative 2 equals x to the negative 2. Or I'll put, because we have an initial condition, we want to use that, we're going to input stuff for that x. So 1 over 4 x squared plus c. All right, so that's that. Now, this, normally you would try to find y. Is there a question? Did I mess anything up? I messed up. Oh, negative 4. OK, good. Thanks. Cool. All right, so normally, good job. So normally you want to try to find y. But if it's something like this, it's a lot of trouble to find y, and they won't expect you to. So what this is called is an implicit solution. So has they mentioned that? Have they mentioned that in class at all? Yeah? OK. So implicit solutions refer to when you have, it's not y equals. There could be x's and y's or constants and functions on either side. Doesn't mean it's wrong. It just means it's implicit. And this is still a valid answer. Unless if it's like y times x, you should move that x over to make it y equals, because that's easier. And then those solutions where you have y equals are called explicit solutions. So like explicitly in terms of x. So that's where that comes from. OK, so now we have this. We have an initial value, which is y of 1 equals 0. So let's do that. I'll do it over here. Y of 1, so we're going to put in 1 for x. I'll just flip the equation around. We'll go 1 over negative 4 times 1 is just negative 4 plus c equals the right side, the left side, which is you put in 0 for here. You have natural log of 1, which is 0. Wait, no, it's not. Natural log of v is, wait, is it? Yeah. All right. Then we got that. So then we can move this over to the other side. And then c equals 1/4. All right. Then the final answer, we're literally just going to erase the plus c, put in a plus 1/4. That's the answer. All right. So is there any questions on that? Or anything involved in the separable? Anything? No? Good. Pretty easy so far, right? OK, do we need to do another separable or no? No? I heard majority of no's. But if you guys want to stay after, you have a question about it, we could do another example. So yeah, I'll be here for a little bit. I'll be here till 9, because then I have to do another review at 9 for Calc 1. I don't really care about them. They're freshmen, so whatever. Sorry, I just erased it. I didn't ask if you guys were done copying, but whatever. So we're done with separable. So we are quarter of the way there. All right. All right. Now, it's going to get a little more tricky. All right. I don't even need this right now. So for linear along with every other kind of problem in this class is a stepwise process on how to solve it. So what I mean by that is you memorize what you do, and it's exactly the same for every kind of problem of that type. So that's how I found this class to be pretty easy. I just memorized what to do and did it for every kind of problem. I know when I took it, it was easier than what you guys did, because it's like online home. We didn't have online homework. There's like phase shifts and all that. We didn't have any of that crap. We just had like straight up, if you know how to do these, you get 100. So I got 100. But enough about that. Now, without even putting in an example right now, I'm going to show you how to solve a linear. It's actually pretty cool because you come up with a formula at the end where if you find the certain components of it, you could just solve the answer right off the bat. But I'll also do an example afterwards. All right. So we know that linears take the form of dy dx plus p of x times y equals q of x. OK. That looks familiar, right? OK. Sometimes they put an a to the x, a times that, or a of x over here, which is just another function that could be there. But when you solve the problem, you end up just dividing that out by all the sides. So it's not really a big deal. So you're gonna, when you want to solve the problem, you end up with this. OK. So the first step, step 1, is to find this thing called mu, which you guys have all heard of. I'm sure they just mentioned it in class, like just out of nowhere. Oh, now you got to find mu, and you're like, what the hell is mu? Where'd it come from? But here's the definition of mu. Mu of x equals the e to the integral of p of x dx. And that's it. That's all mu is. And usually they'll give you a function with 1 over x or 2 over x, something like that, where you end up integrating that. You get some form of a natural log, and then you can have some sort of cancellation between the e and the natural log. So it makes it a little bit easier. Sometimes they don't do that. They try to screw you over by putting in like plain old x, where you have e to the, then you have x squared over 2, or no, you'd have, what's the, yeah, you'd have, yeah, x, yeah, 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 yeah. Long day. All right. All right, so once you have mu, the next step is you take mu and you push it somewhere else. No, you multiply it by the entire original equation. So you're going to end up with mu of x times dy dx plus p of x times y. And then times, I'm going to put mu of x q of x. That rhymes. Cool. OK, I rhymed of x with of x. All right. You got this whole thing now, right? Now here's the not tricky part, but something that not many people remember. And I don't even know how they taught it in class. I don't even know if they taught you it. They taught you it this way, basically, right? So sometimes they go in like a theory. Does anybody have Brady? He still teaches, right? OK, good. Good, thank God. I'm not going to make fun of him, but he's a great professor. But he goes in like theory and everything behind it, and he's like, oh, you end up with your answer after all this like quantum chemistry, calculus, and physics, everything. And it all ties in. It's all one entity, whatever. And screw that. We're just going to solve it. So once you're at this point where you have mu of x times the left side of the equation, you could just say the left side of the equation, hear me out now, left side of the equation is equal to the derivative in terms of x of mu times y. Dead silence. That's it. Any questions on that? I'm going to say it like a million times. So the left side of the equation, once multiplied by mu of x, you could assume that this is equal to the derivative in terms of x of whatever mu of x is times just y. That's it, just y. Yeah, and if you were to, you can check your work. If you're an overachiever, you can implicitly differentiate this, and you'll get out this. So I actually did it before, and it works. So I didn't just take their word for it and just teach everybody in the world that. All right, you got that. Now the right side of the equation is just the right side of the equation still. So that's boring. Q of x. So now, look, there's a derivative. What do you want to do to a derivative to get rid of it? Integrate it. So we are going to integrate both sides, very, very similarly to separable. So there's a little common factor here. All right, so if you integrate a derivative, what happens? They go away. So you just end up with mu of x times y. And you integrate that, and we don't have values, so it's just whatever. So now look, this is just mu of x times y. You can divide mu of x and put it on this side. And look what this is. That is a formula, without even doing any of that other stuff. If you memorize this and get mu of x, you can solve the equation right there. Yep? Yes, but that would happen after you integrate this. We don't have any value. This is like a template example of like, we didn't actually put in any values or functions yet. But once you do, you integrate them, and then you have a plus c on the top somewhere. Good question, though. OK, so doesn't that blow everyone's mind? This is like the formula for the equation. This is like the formula for it. You don't even have to do any of the other stuff. But I'm going to do all the other stuff. Yep?
What exactly happens to the d over dx?
Oh, it cancels out with the integral, because we're integrating both sides. So if you take the integral of a derivative, they cancel out. OK, any questions on that? OK, now we're going to do an example. I'm going to go through this whole thing. I think I have room over here. So I'll just, whatever. No more questions? We sure? All right, cool. All right, what example do I have? I have a bunch. Hopefully I have some exact linear. Here we go. There we go. Okay. All right, here's the example. So you have dy dx equals 2y over x plus x squared cosine of x. And look, it's an initial value problem. Y of pi equals 2 pi squared. All right. First step is to determine what it is. It's linear, because I'm going over it with linears. But it's good to know about linear and Bernoulli are very similar. The only difference is that in the q of x of Bernoulli's, there's also a y term there. But here, you can kind of see everything already, even though it's not in the exact form that we want it to be for linear. You can see a dy dx. It's there. You can see a plus p of x, y, is with a singular y. That's good. And then there's just some function of x over here. We'll make it q of x. All right, so now the first step would be to rearrange this to make it look just like this original form. So we will move over the 2y over x to be minus 2y over x. And then we'll make it equal to x squared cosine of x. All right, good so far. Now, first step. What was the first step? Nick, what was the first step? Find p of x. Good. All right, so find p of x. P of x is equal to everything in front of the y. That includes a negative sign. That includes a natural log, anything that could be in front of the y that is not a y. So in front of the y, we have a negative, we have a 2, and we have an x. So we're going to put negative 2 over x. Good. Next is to find mu, because we have the p of x in order to do that. Bless you. So we have mu of x. Mu of x is equal to e to the integral of p of x. That looks as an s. I can't write good integrals. The kids I tutor, they write integrals like, it's like really like extravagant, like all that stuff, and it's got like things on it. It looks really nice. I just write s's. I just stretch out an s, and that's my integral. All right. I'll try to make it look nice. Ooh, look at that. All right. And I'll take out the negative 2, and I'll put 1 over x dx. Just like that. All right. So now we have that. We can solve. We can do some math there. We can't just, we don't want to leave it like we did over there. This equals e. And now the integral of 1 over x is natural log. Good. So we have a negative 2 times the natural log of x. Now, important thing here, since we're solving for an integral, we have an integral, we don't need to put a constant here, like you may think. Why? Because you put one in later. I don't actually know why you don't put one in here, but I know there's one later, so that's why you don't do it. So don't put one in here. All right, so that's it. Now, this is something that you learned in algebra, way back in algebra. I don't know, it's like rules of logs. So you can simplify this even more. How do you do that? So we have a negative 2 in front of the natural log. Most people will be like, oh, you just cancel out the e and natural log, and you get the answer is negative 2. Duh. No, it's not. Because there's a rule of logs where the coefficient of the natural log, or even regular log, you move it over to the exponent of the x. And that's a thing. And that's a thing. So that's your thing. And then you have a natural log of this would be x to the now negative 2. Then you can cancel it out. The way I think about this, and don't forget it, is if you literally tried to cancel out by drawing a line through it, you would encounter a problem because the 2 is there. So you can't physically draw that line through them, so you have to get rid of this somehow by putting it in the top. Then you can physically draw that line. I know that might make sense to some of you, but not others, but I'm weird, so whatever. All right, so this becomes e to the natural log of x to the negative 2, which now they can cancel out, equals x to the negative 2. So this is mu of x. Okay, good. Now we could basically just, we win. We're done. But I'm going to go through the rest of it. All right, so now next step is to multiply. Multiply. I was thinking mu and multiply at the same time. So you're going to multiply mu by the entire equation. So let's do that right now. So x to the negative 2 times dy dx minus 2y over x equals x squared cosine of x. And some of you people already knew this already, but then look, negative x to negative 2, what happens there? They cancel out. Makes our life a lot easier. All right. So, everyone still see, right? Yeah, of course. Why did I even ask that? All right. So, cosine, we got that there. Good. So now, what can I say about the left side once I multiply it by mu? That the left side is now equal to the derivative in terms of x of mu, which is x to the negative 2, times y. And that's it. And now this is equal to the right side, which is simply just cosine of x. And now we can integrate. Integrate, integrate. If you integrate a derivative, what happens? Cancel out. X to the negative 2 times y equals the integral of cosine of x. All right, integral of cosine of x, remember from trig, it is sine, right? Yeah. So we got sine of x. And now we do have to add the plus c. So that's important. Why do you add it now? Because you didn't add it before. All right, now we are trying to look for y equals to get an explicit solution in terms of x, which we can easily do by dividing by x to the negative 2 over x to the negative 2. And that is your answer. But we have a initial condition, right? Yep, an initial value. OK, one more little side note. When you have a constant, and suppose you move something over from the other side, and you have like, if it's like a 2, the professor might have written just like plus c again. And you're like, where'd the 2 go? If you're multiplying it by a constant times a constant is another constant. So that's kind of explanatory. But if you're multiplying it or dividing it by a function, anything that changes over an x or a y value, that's when you have to keep it there. So if I were to simplify this, I would have sine of x over x to the negative 2 plus c over x to the negative 2. It wouldn't be right to just put like plus d or some other constant, because this value, this term, the c over x to the negative 2, will change when you change x. That make sense? All right, cool. Because I know when you guys, like, with me, when I was nervous, like doing the test, like, I was panicking, I saw that, I'm like, oh, it's c, it just becomes another constant, whatever. But it's not the case. All right, now, enough of chit-chat. Now we're going to put in the initial value. So we have y of pi. So we're going to put in pi. That's going to be, I'll flip the equation. I'll do sine of pi plus c over pi to the negative 2. Pi to the negative 2. I can take this pi to the negative 2, bring it up, make it pi squared on top, like that. And now, since you have, whatever, we'll just solve it. Hold on. Y is going to be equal to 2 pi squared. OK, now we can multiply this in. So we have, or sine of pi, what's sine of pi? Sine of pi is 0. Good. So it's gone. And now we're going to have c times pi squared equals 2 pi squared. All right, now c is going to be equal to what? 2, right? Good. I hear some like chatter. Did I mess up anywhere? Or no? OK, good. Let me know if I messed up, because I probably will. Yep, question.
I just have a question.
Yeah.
So the part that always gets me is that I can never figure out like what's supposed to be like the p term or whatever.
Mm-hmm.
So at the very beginning, when you then switched over like negative 2y to the x, like why did you specifically choose that one? Like what went through your mind that you knew that?
Right. OK. Good question. So when I look at this, like things to move over, make it look like it's in the form, the p of x is always going to be in front of a singular y. That's it. If you had, suppose we were doing Bernoulli like we're later on, you might have 2 terms with a y. One of them will have a y, one of them might have a y squared. You know that this one has a singular y, that's the one you put. That's going to have the p in it. All right, good. And then the other one will be the q, but yeah. But if we have another y there, we'll do Bernoulli and do it up like that. All right, so c is equal to 2. Now we can put in c for this value right there. So now we have, this is the answer. Y equals sine of x plus 2 over x to the negative 2. OK, is there any questions there? No. It's a good sign. It's either a good sign or a very bad sign. Hope it's a good sign. All right, now I could do this now because I'm cool. I can move it up, and I can move this one down. All right, That's awesome. So, do you guys need me to go over another linear right now? No? Okay, good. Now I'm going to go over a Bernoulli. So this is like linear on steroids. Who's ready for this? I am. All right, let's go linear. I mean Bernoulli. Okay, now here's a little disclaimer. I solve Bernoulli different than everybody else does. Not everybody else, but most people. They taught it in class. I don't do it that way. Maybe they taught it, maybe they didn't teach it well. Maybe you want to learn a different way. But if you guys are like gung-ho on Bernoulli, you get every single one right with whatever method you're doing, keep doing that method. The point of me is to make sure you get everything right. If you guys are lost in Bernoulli, follow me. But other than that, if you guys know it, go for it. Do your own thing. You could sleep now. I don't care if you know it. All right. Bernoulli. Apparently, I don't know how to spell Bernoulli. I think is it OU with the thing and the thing? And I learned last year there's two L's. I heard last year there's two L's. All right. So, a Bernoulli is like a linear on steroids. So the form of it is going to be a linear with stuff added on, with a little more muscle. dy dx plus p of x times y equals q of x times y to the n. Now this y to the n is bad. We're gonna make it. So the idea of this is we're really getting something like this that I'm trying to think now. Like why would you make that? And like just to screw us up and have to do another like whole like 40 minutes of steps just for this little term, whatever. I don't like this, but we'll do it. All right. So the point of a Bernoulli is to make it look like a linear and then just solve it. That's really what we're doing. So we're going to substitute in, for every y you see here, we're going to substitute in some form of v. And that's going to be our new dependent variable. Or, yes, dependent variable. That's what y's are, right? Yeah. Our new dependent variable. And then with that dependent variable v, it's going to now look like a linear. Then we could easily solve it, just the way we did before. All right, so let's do an example. And I don't think there's a formula like I did for the linear. There's no like formula like you could just find mu and then just do the thing, because it's a little more complicated. All right, examples. All right, so we're going to go y prime equals 5y minus 5t y cubed. And there's no initial value. Good. All right, cool. Yep. All right, where's Caruso? We did this already. We just went already. So I'm sorry, but you get to learn it again. All right, cool. So first step, when you make it look like that. All right. So kid in the back who asked the P question, which one of these terms would we move over?
It's going to be the 5y.
Boom. Exactly. Good job. All right. It's a 5y. We're going to minus subtract that. And I'm going to make this y and turn it into a dy dx. Wait, question anywhere? No? Yeah? Minus 5t y cubed. Yeah. Sorry, that's a t. Where's the eraser? There it is. I might accidentally write x's, but just correct me. Whenever I write an x, just say t. Be annoying like that. I don't care, because I want to get it right. All right. So we're here. I'm going to make this into a dy dx just to make it look familiar. dy dt. Cool. And then we'll make this equal to negative 5t y cubed. Just like that. All right. OK, cool. So now we need to do some stuff because we have this here. If we didn't, we could just solve it like a normal linear, but we can't. So what do we do with this y to the n? First, let's identify n. N equals 3. Good job. We identified n. Now, what do we do with it? Now, this is just, I don't know who invented this, but it's crazy how they came up with it. But the substitution value that we're going to use, v, it has a relationship with y. And the relationship is v equals y to the 1 minus n. Why is it that? I don't know. So now we're going to make, we know what n is, so v now equals y to the negative 2, which is the same as 1 over y squared. Now from here, I think everyone's way of solving this kind of problem is the same until here. This is where my method diverges a little bit, so if you get confused, please ask questions. And if you don't want to listen to me because you know how to do it already, don't listen to me. All right, so v equals 1 over y squared. From here, I like to find y. Personally, I want to find y. I like y. I want to find him. So we move this over and move it back and take the square root. So let's do that. So we're moving y squared equals 1 over v. Now we're going to take the square root of each side. So that square goes away. And we're going to have this. Y equals the square root of 1 over v, which can be rewritten as 1 over v to the 1/2. Just like that. Yep. How do you know v is positive? What do you mean? Oh, like under the square root? What do you? I don't know. I don't know. I have no idea. It could be negative. I mean, I didn't get rid of the square root. It's still there. Oh, you mean like plus or minus? Yeah, it's a really good point. I don't know. It's just like, I never actually tried to make it negative, but I don't want to try. Let's not try. I heard someone say let's not try, so let's not try. That's a very, I don't know. I'll do it later. I'll do it later. I'm not gonna do it later, but I don't know. I want to do it. I actually want to do that later. That's a really good question. No one's ever asked that before. That's interesting, and it makes mathematical sense. So I like that. All right. It's positive now, so let's keep it positive, or whatever. All right. So now we have y equals 1 over v to the negative 1/2. All right. So the idea, just like for doing a u sub or any kind of substitution thing, you want to substitute everything you see a y in. That includes a dy dt or just a regular y. Substitute that with something with a v. So we now have y equals 1 over v to the 1/2. So that gets rid of this v, or this y, and this y. Now we just need this, a dy dt. So my instinct, my mathematical instinct, would tell me to derive right here. So y equals 1 over, I'm going to put y, I'm going to rewrite it as v to the negative 1/2 to make it easier to derive. So now we can put in dy dv now, because we're differentiating this, equals negative 1/2 v to the negative 3 over 2. All right. Now, this step, I kind of like, when I learned this myself, I kind of like forgot what to do here because it just didn't make any sense. I'll just tell you what I do. All right. So here we're looking for dy dt, right? We have dy dv. So if you I just thought of this myself, just multiply at both sides by dv dt. And then the dv's would cancel out. You literally just get that. You get dy dt. Now, why did I do that? I don't know. It works. Just if you don't know what you're doing, do that. And just, I have it in the notes. I like literally wrote out step 1, step 2, step 3, and I wrote exactly what to do, and it will get you the answer every single time. But do I know the theory behind it, like Dr. Brady does? No. Okay. We have this. We have dy dt is this thing. We have y equals that thing. We are ready to substitute in for this y. All right. So our dy dt is now equal to negative 1/2. I'm going to put 1 over v to the 3 over 2 times dv dt minus 5 times y, which is, I'm going to rewrite it as 1 over, I'll just put 5 over v to the 1/2. Okay, now equals negative 5 times t times y cubed. So y cubed is just going to be 1 over v to the 1/2. Whole thing is going to be cubed. So then we can rewrite this as 1 over v to the 3 over 2. Okay. Yeah. All right. Everybody get it up to this point. If not, ask questions. Cool. All right, so now our job is done with getting it to look like a linear. Because with the right dividing stuff out, we can make it look exactly like a linear. So we have a thing in front of the dv/dt. What do we do with that thing? Divide it out. So we need a term that could divide this out. So that could just be literally just undoing it. So multiply the entire equation by that term. It is negative 2v to the 3 over 2. Because that would literally undo everything and just make it 1. So we have negative 2 times v to the 3 over 2. Everybody got how I picked that value? Okay, good, because I want to undo everything that's in the negative, the denominator, and make it just 1. Cancel everything out. Okay, so once you multiply by this term, it cancels everything out, and you just have a dv/dt. Multiply it by the second term. Negative 5 times negative 2, positive 10. So you have dv/dt plus 10. Then you have v to the 3 over 2 over v to the 1/2. What does that equal? Just regular v. So now it's looking just like a linear, but we have v's instead of y's. Now a good tip, if you guys are doing this on the test and you don't get a singular v at this step, you might want to backtrack and check what you did, because you probably did something wrong. Because you need this v to just singularly be a v, or else you can't solve it linear. And similarly, on the right side, if this v doesn't cancel out and make it just no dependent variable on the right side, then you probably did something wrong. So now we're going to do the right side, which is negative 2 times negative 5, which is also going to be a positive 10, times t. And then you have v to the 3 over 2 over v to the 3 over 2, which is just 1. So that cancels out. And this looks like a nice, clean, easy linear. All right, so let's solve this linear. Any questions up to this point? No, good. All right. So first things first. Nick, what do you do? Boom, p of x. P of x equal, oh, p of t. No one corrected me. What the hell? P of t. P of t equals everything in front of the v, which is just 10. Now we need to find the mu of t. Mu of t. Move it up. Mu of t equals e to the integral of 10t. Okay. Now, this is one of the ones where they didn't help you out at all by putting a natural log in there or making it look all nice and cancel out. It is just simply just like all screwy like that. So the integral of that, did I mess up? No, I messed. Yeah, dt. I was like, damn, that's gonna be hard. But I'm like, okay, not that bad. So this is gonna equal e to the 10t. Okay. Now, next step, exactly the same as every other kind of linear ever known. Multiply mu by the entire equation, not the entire original equation in this case. That wouldn't get you anywhere. Multiplying it by the original linear equation after doing all those steps to get to that point. So we're going to multiply mu by that original linear. I'm short. I'll move it down. E to the 10t multiplied by dv dt plus 10v equals 10t times e to the 10t. All right, now what can we say about this left side? The derivative in terms of t, in this case, is equal to mu times, not y now, but just v. So I'm going to write that down. d dt of mu, which is e to the 10t, times v is equal to now just the right side. T. All right. Okay, there you go. So we have a derivative. What do we do to undo a derivative? Integrate. Let's integrate. Integrate that. Goes away. Integrate this side. Now, something like this, you'd have to use integration by parts. But I think for this, they'd give you that on the equation sheet, on the integral sheet. They'll probably give you something like integral of at e to the t. Like they'll put like a constant arbitrary thing there, and they'll give you the answer for it. But I'm gonna do a little magic trick, and I'm gonna find it right now. There's this thing called maybe you guys does anyone know tic-tac-toe method? Does that ring a bell for anybody? No? But maybe you've seen, I don't know. Maybe you've seen it. I learned this in high school. It's really interesting. All right, so you basically just write plus, minus. I think that's enough. And then if you have a term that can derive to 0, by that I mean like a term like 10t, excuse me, 10t, if you keep taking a derivative, you get 10 and then 0. Or for like anything with basically t to any power, it basically derives to 0, except if it's a negative power, but whatever. Then you use regular integration by parts. But, so you put that in the left side, you put 10t, and then something like e to the 10t, you put on the right side. And then you basically derive this column all the way down to 0, integrate this column until this one gets to 0, and then you cross multiply. So that's weird. It's not going to be on the test at all. You don't even need to listen. I don't want to confuse you, but this is just what I'm doing. So 10, 0. E to the 10t, bless you, over 10. E to the 10t over 100, bless you. Put bless you, no. OK. Boom, that's it. Yeah. So what this means is that the integral is going to be equal to, I'll write it over here, equal to positive 10t over e to the 10t over 10. So then this would cancel out. Minus 10 times e to the 10t over 100. So then this would be over 10, and then the 10 would cancel out here. So that's your integral, and then plus c. All right, so they would give you that. I did cool, fancy math. I'm a math magician. No. Now we have the left side, which is e to the 10t times v. Now this is simple because we integrated the derivative. That cancels out, so we're just left with this. Are you Snapchatting me? Or? Oh, OK. I'm not that popular yet, right? All right, so e to the 10t. That cancels out. And it goes, and we put it in the denominator here. So e to the 10t. That's sloppy, but we can clean this up. I'm going to bring it up here. I'll bring it up here. Bring it up there. OK. So we have an e to the 10t in the denominator. So we can take this and we can cancel out with this one, and put it in the denominator of the c. Remember, we can't get rid of it because it is a function that changes with t. So let's do that. So we have the left side is going to be v equals t minus 1 over 10 plus c over e to the 10t. OK. Does everybody understand how I did that? Yeah? Good. Good. All right. So are we done yet? No. Because what was the original equation problem? It had y's and t's. We have v's now. So when you go back to what we did like 10 minutes ago, the relationship between v and y. And now we need to use that to turn this v back into a y. So we know that v equals 1 over y squared. Get rid of that v, 1 over y squared. OK, now we can kind of easily find y. We can move this y squared over, move this whole thing into the denominator, and take the square root of each side. And then you end up with y equals 1 over t minus 1 over 10 plus c over e to the 10t square root of that whole thing. Or you just could put square root of the denominator, because square root of 1 is just 1. But that's the answer. OK, is there any questions on that whole thing with Bernoulli's? Silence. OK, OK. I'll take that as you guys understand it. If not, yeah, question. Now, again, I don't know. This is right, but you know what? I guess you should put plus or minus. Yeah. Yeah. So I guess, would that would that cancel out the problem we had over here if it's plus or minus, just putting the answer plus or minus? Maybe. I don't know. Probably. So that's good. But I don't know if I suggest putting plus or minus, because, yeah. That would give you an implicit solution, kind of. But yeah, it's not wrong. But I don't know what they would do. I don't know how anal they are about grading. So yeah, you could try it. Any other questions? Yep.
Did you find an existence interval for that?
If they ask for that, I mean, yeah, I don't see why not. But not on a test, because you need to find where this denominator equals 0, which, from the looks of it, is complicated. So, and they'd have to give you an initial value also to do that. So maybe on like some convoluted homework assignment they give you that, but not on a test. Good question. Was there a question in the back over there or no? No? Okay. Okay, cool. I don't want to do another one, but I will later. Nick, you have a question? Is this your hand? Does it hurt? Good. All right. All right. So that's Bernoulli. Now, only one more thing, and then you guys can sign in. You can leave. You can go eat food. You can go eat. You can do whatever you want, or you can study. But who wants to do that? All right. So we're done with linear and Bernoulli. Exact. I'll go here with exact. All right, we ready? We ready? One more kind of problem, and then you guys can just shoot questions at me, and yeah. Oh, I forgot to say something. We got SITV filming this stuff. If you guys did notice, I should have said that in the beginning. I'm really sorry. They're really cool. Yeah, no one noticed the big camera, I guess. I don't know. Maybe I'm that entertaining. Probably not. But so this will be on the Facebook page, right? I think it'd be on the it'd be on YouTube, and it would be on the SIGEP the review page also. Yeah. So that's the thing. That's pretty cool. Thanks, guys. All right. Now we're going to do exact. So, exact. I'm going to write down the example, talk about it, and then we'll do it. Minus 2 dx plus All right. All right. We ready? We ready? We ready? Are we ready? Yeah, Brer. Okay. I'll do that. Good. Okay. We ready? All right. Exact. So I wrote down an equation. I wrote down an example. So Brer asked a really good question. What is the general form of these kind of equations, of exact? And the answer to that is, it looks like some function of x and y, really. It could be anything. So I'll write p of x comma y dx plus q x comma y dy equals 0. Now, if you see it in something like this, or you have this on one side, this on the other side of the equal sign, exact should raise a red flag. Okay, it could be exact. But the first thing you need to do is check if it's exact for every kind of problem. Even if it says solve the exact differential equation, they might throw in a curveball and be like, oh, it's not exact, you can't solve it. And then you'll just try to solve it, and you won't get anywhere. And then Dr. Brady will be like, haha, gotcha. But all right. So it looks like this. So the first thing you do is to check the diffie-q to see if it's exact. You always have this association in mind for the rest of the problem, except for this part, where you have m is associated with x, and n, as in Nancy, is associated with y. I noticed something. Wait, never mind. I'm not going to say that. That might offend somebody. With the world we live in, everything's offensive, so I'm not going to say anything. All right. So the way you check it. So I'll write to check. I always write everything that has a dx. I'm kind of like, I'm sloppy right now. I want to get structured. All right. So the term with the dx in front of it, the first thing I do is label it as m. Like that, m. And similarly, the term with the dy, I label it as n. All right. So to check to see if it's exact, to check if exact, you're going to do dm dy is equal to dn dx. And for this part, it's like, it's a, what do they call it? Partial derivative. So you use that crazy fancy d. So that's a thing now. All right, so you check if this is true. So let's go ahead and do this and get it out of the way. So you have dm dy. So we're going to take m, differentiate it in terms of y. So that's going to be 2y. Yeah, that's it, 2y, right? OK. Now dn dx, everything in terms of derived in terms of x is going to be 2y. Easy. Because everything else cancels out because it doesn't have an x in it. All right. So any questions on checking? You can see these are obviously equal. So is there any question on checking? No. Good. OK. So now you take this association that you just used with m and y and n and x, throw it out the window. You know that everything with the dx next to it is an m. Everything with the dy next to it is an n. All right. So 2 more things that that you should like memorize when you do exact equations is that you have the main. OK. So the main function that like is our answer function is going to be called big F. It's like capital F. So if I write the derivative of big F in terms of x, that equals m. So that's going to help us later. And similarly, the derivative of the big function in terms of y is going to equal n. So these things are very important when it comes to solving it in like the next couple steps. So the first step is we want to get from here, we want to get, I call it a template of what the big F looks like. So the way to do that, you could do it multiple ways. I know some kid does it a different way where he does it the opposite way. I'm going to deal with m first. Some people deal with n first. I don't think it matters as long as you get the right answer, as long as you end up with the same answer. So I'm going to deal with m first. So I'm going to take m, and I am going to integrate it in terms of x to get f. Because if I did integral here, the integral and derivative would cancel out. It would be f equals the integral of m. So I'm going to take the integral of 3x squared plus y squared minus 2, which is m, and I'm going to take that in terms of x. And this is going to be equal to just x cubed plus y squared x minus 2x. Right? Yes. OK. Now this, as it gets a little tricky. All right. This is the derivative of m in terms of x. Integral, sorry. With every integral, you have to add a constant, right? In this case, because we're dealing with 2 variables, x and y, and we're only integrating in terms of one of them, which is x, the constant could be not only a constant, but a y. That make sense? Because you're holding the y constant throughout this entire equation. So the 2 is a constant, the y is a constant. So that means any constant or any y could be a constant. So we need to account for that when we're integrating m in terms of x. We need to have a constant which could have y's in it. So we like to write plus g of y, which is g of y could be 2, it could be 1, it could be 0, it could be natural log of y times 50 billion, doesn't matter. It just can only have y or constants in it, no x's. And we're basically from this point, this is equal to f of xy, which is the big F, big answer. Basically from this point on, we are doing some like derivative, integral, back and flip-flop, back and forth to find this g of y. And that's really it. So we have this. Let's find this g of y. Now, we have big F. We could look at this definition right here and say, oh, if I take the derivative of big F in terms of y, I get n. Let's do that. Derivative of this in terms of y. So I'm going to do df dy equals. This would cancel out. The x cubed would cancel out. You have 2yx. The minus 2x will cancel out. And you have g of y, which the derivative of g of y would just become g prime of y, because we don't know what g of y is yet. Now this is df dy. What is it equal to? Directly equal to n. So we can take n and push it this way. Put it right there, equals. So it equals 2xy plus 6y minus 3. All right. Well, look, a lot of these questions, you'll have something that cancels out with the g prime of y to make it simpler. If you end up with something really, really complicated here that looks almost too complicated to be right, you're probably right. It probably is too complicated to be right. So always check your work and make sure it's something kind of smooth going on over here. So you have 2yx, this cancels out. So now you're just left with g prime of y equals 6y minus 3. Just like that. Cool. Any questions up to this point? No. Good. All right. So now, because we're so good at math, when we see a derivative or a thing with a derivative, what do? Integrate it, because we want to get rid of that. So we're going to integrate this g of y and this side to make it to integrate the g prime of y, and make it a g of y. And we're going to use that. This would be our constant, like our plus c kind of thing, and we're going to put that in here. All right, so then it's going to be g of y equals integral of that, which is going to be 3y squared. Yeah. Minus 3y. Yeah. Okay. So this is our g of y. Just like that. Now we can erase this g of y. Since we know it already, we can put in 3y squared minus 3y. And I forgot something. Since you integrated here, have to put the plus c. Because at this point, we integrated in terms of x and y. There's no room for any other variables to be constants, because we accounted for both of them. So at this point, the only thing that could remain a constant is a number, a constant number itself. So that's where we put the plus c in at the end. It's going to be plus c. And usually, the way they want the answer written is either it's equal. They want it equal to c, right? Didn't someone? Yeah, they want it equal to c. So you put equal to c. I think on my first test, I put equal to 0, and they gave me a point off. So, but that was like 2.5 years ago. But they still did it. Okay. Is there any questions on exact? I know that was kind of different. Okay. Any questions at all? Oh, yep. Oh, sorry. It's this. Yeah. Okay. Is there anything else? Well, I think that's it. I mean, I covered the 4. If you have questions, you can. What time is it? Oh, yeah, we're good. If you have questions, you can stay. Like other like I'll do examples on the board.